Hey, hello. Welcome to week 10. So this week's agenda is first, examples and non-examples of homomorphisms. And two is to apply a certain theorem in your textbook to the ones from item one that are examples. So the maps that actually are examples of homomorphisms because the theorem only applies to homomorphisms. So first, let's look at some examples and non-examples. So first, an example. The map F from R star to R star again, sending X to the absolute value of X. Note that R means the group operation is addition, whereas R star means you omit 0 and make the group operation multiplication. So you have to omit 0, right? Because 0 doesn't have an inverse under multiplication. And multiplication. This is a homomorphism. Recall that in general, to check if F from G to H is a homomorphism, you check if F of A times B equals F of A times F of B. Note that here times means the operation in G, whereas on the right-hand side, it means the operation in H. And always when I say times for a general group, it's referring to abstractly just its group operation. So times could mean plus, and it does in certain situations. So it's not just, it doesn't, I do not mean multiplication in like the integers. I just mean abstract group operation. So here, anyways, it means the operation H. So that's how you check in general if a map is a homomorphism. So we'll do that here. So for example, F of A times B is equal to the absolute value of AB, whereas F of A times F of B is the absolute value of A, absolute value of B, and these are equal. And that's just a property of absolute values. Hence, F is a homomorphism. Okay, second example. F, it's a map from Sn to the group containing 1 and -1, which is a group under multiplication. Right? 1 times 1 is 1, -1 times -1 is 1, -1 times 1 is -1. It's a group. It's a group under multiplication. Multiplication of, normal multiplication that you knew of before you took group theory. So, and the map F is this map, which takes a permutation to its sign. Okay, F is a homomorphism. Because F of sigma tau is equal to the sine of sigma tau, while f of sigma times f of tau is equal to the sine of sigma times the sine of tau, and these are equal. It's just a property of sine. It's a property that I don't know if you guys approved it. I won't prove it because the proof is a bit complicated. It's easier to just, and it's not that enlightening, I would say. As in, like, the technique of the proof won't really benefit you in many situations. So it's best to just remember this result. Although, if you're interested, go see the proof of it. So this is a homomorphism because f of sigma tau equals f of sigma times f of tau. Okay, another example. And this is on page 198 of your textbook. This is the map F from C star to C star, which takes Z to the 4. And as with R, C means addition, C star means omit 0, and make the group operation multiplication. Okay, so we check if F is a homomorphism as before. F of ZW is equal to ZW to the power of 4. F of Z times F of W equals Z to the 4 times W to the 4. And these are equal in the complex numbers. So that's another example. The last example is a bit complicated. And it's kind of a universal example, as in, and this is something you'll learn. The first isomorphism theorem, basically, you can interpret it as saying that the example I'm about to give is a universal example of a homomorphism. What I mean by universal example is every homomorphism is essentially this homomorphism, in a sense. So let H be a normal subgroup of G, then F from G to G mod H, which takes little g and g to the coset GH, is a homomorphism. So we check that the condition holds. So take two elements, multiply them. So f of G1, G2 is going to be G1, G2, H, whereas f of G1 times f of G2 is G1H times G2H, and this is in G mod H, and that's just equal to G1, G2, H. And that's just the definition of multiplication in G mod H. So there's equality. And what this says is taking mod something is a homomorphism. And you already were used to this in modular arithmetic. So what this says is this example. It reflects the fact that modding out by something is a homomorphism. You already are used to this. All right, you've already seen this in modular arithmetic. So consider the map f from z to zn, which takes a to a mod n. This is a homomorphism. So this map is a homomorphism because f of a plus b is equal to a plus b mod n, whereas f of a plus f of b is a mod n plus b mod n, which is a plus b mod n. I guess this notation mod n that I'm using is a bit non-standard. The more common thing to do is write either a plus nz for the coset. So ways to denote cosets mod n. You can write a plus nz, that's one way. Another way is just doing this or something. I can't think of any others right now. There's probably others too. Yeah, so this is a homomorphism. So you can add before you take mods, or you can add after, and it'll all work out. The answer won't change. So that's the last example, I guess, that I want to do. Here's a non-example. F from R to R, remember R now means addition, x to x squared. This is not a homomorphism. Why? So f of a plus b, and remember this is the group operation in R. So f of a plus b is a plus b squared. F of a plus f of b is a squared plus b squared. These are generally not equal. So for example, when a equals 1 and b equals 2, they're not equal. So we have f of 1 plus 2 is f of 3, which is 9, whereas f of 1 plus f of 2 is 1 squared plus 2 squared, which is 5. These are not equal. So f is not a homomorphism. Here's also kind of a non-example. I mean, I say kind of because it's not an actual concrete case of something, but it's something that generally isn't an example of homomorphism. But sometimes it is, but generally it's not. So the non-example is the map F from G to G taking a power. So G goes to G to the N. This is a homomorphism if N equals 1, first of all, because then it's just an identity map. Or if G is abelian. So if G is abelian, then it's a homomorphism. Right? Because if G is abelian, then f of G1, G2 equals G1 times G2 to the N, which is G1 times G2, which is G1, G2 times G1, G2, and you repeat it N times. That's always what power means. And then if you do f of G1 times f of G2, you get G1 to the N times G2 to the N. So that's G1 times G1 N times, then times G2 times G2 N times, and these are equal. So if G is abelian, we can move the G1s and G2s around. So if G is abelian, then in a product, you can move the terms around, you can reorder them. So maybe that's a better word. We can reorder the G1s and G2s. We're going to need quotations. So we can reorder the G1s and G2s. So G1, G2 times G1, G2 n times is equal to G1 times itself n times, and G2 times itself n times, right? Because you just move the terms around because it's abelian. However, if G were not abelian, we cannot just reorder the G1s and G2s. So generally, f of G1, G2 equals f of G1 times f of G2 will not hold. I.e. f won't be in homomorphism. And here's actually a result that doesn't use the word generally in it. So it actually says f will not be a homomorphism if G is not abelian in the case where n equals 2. In the case where n equals 2, we actually have that f G to G, sending little g to G squared, is a homomorphism if and only if G is abelian. I don't know if this holds for n equals 3 or higher or not. I invite you to think about that. And if you figure it out, let me know. But I don't know off the top of my head. Can I figure it out? I'll give myself 20 seconds. Yeah, I don't know. Probably not. But with n equals 2, it is indeed an if and only if. So you already know it's an if. So if it's abelian, it is a homomorphism. We just showed that. The question is whether it's an only. Can it be like a homomorphism in some non-abelian group? When n equals 2, it can't be. So when n equals 2, so why is this true? Well, we already proved the if direction. For all n. For the only if direction, suppose F is a homomorphism, then for any A and B in G, we must have the condition that you always check for homomorphism. It should hold here. So we must have f of AB equals f of A times f of B. And f of AB is equal to, and this should hold for all A and B in G. Well, f of AB is equal to AB squared, which is equal to AB, right? You just do AB times itself. F of A times f of B is equal to A squared B squared, which is AABB. So for f of AB equals f of A times f of B to hold for all A, B, and G, we need that AB equals AABB for all A, B, and G. But in this equation, you can cancel out the A and B. The leading A and the final B. The initial A and the final B. i.e., so an AB equals AABB, you multiply by A inverse and on the left and B inverse on the right. So this is equivalent to A inverse AB, B inverse equals A inverse AABB, B inverse, which is equivalent to BA. Well, I'll write it out. So I'll actually write the full product first. And of course, a pair of inverses will cancel. So A inverse A and B inverse will cancel. So this is equivalent to BA equals AB. Hence, f of AB equals f of A times f of B for all A, B, and G is equivalent to BA equals AB for all A, B, and G. And that's exactly what it means for F to be abelian. I mean, for G to be abelian. So that's how you prove that. Please make sure this canceling argument I did is like second nature to you. So even though I made it look complicated, that was just to justify it. But like if you see A times something is equal to A times something, those somethings need to be equal. Like the point is you can divide in a group That's the whole point of having inverses. So like, it's like if you have an equation, 2x equals 4, you divide both sides by 2, you can divide both sides by a, but there's a direction to it because it's not abelian. So you can divide by a on the left, you can divide by b on the right. That's what we did. So there is like a subtlety to it, but the point is you can cancel out a's and b's. You can cancel out elements, groups. That's like that's due to the fact that groups have inverses. So, and then let's do a concrete case of this. So an application when G equals, or an example, I guess. An example when G is equal to S3 n equals 2, the map F from S3 to S3, which takes permutation sigma and squares it, is not a homomorphism because, by the way, I should say this is not the kind of result you would need to remember. So you don't need to remember that G goes to G squared is a homomorphism if and only if G is abelian. It's more of a result just to test your understanding of group theory, but it's not unlikely to be applicable to specific problems. But yeah, here's an example that gives us some confidence that our reasoning is correct. So sigma goes to sigma squared, and it's not a homomorphism because S3 is not abelian. And what our reasoning showed is if you take any two elements A and B that don't commute, then f of AB equals f of A times f of B shouldn't hold. So we'll just do that for S3. So it suffices to find A and B such that f of A B does not equal f of A f of B. So an example is, so one possibility is A equals 1, 2 and B equals 1, 3. So f of 1, 2 times 1, 3 is f of 1, 3, 2. And by definition, f just squares the permutation. So that's f of 1, 3, 2 squared, which is 1, 2, 3. On the other hand, f of 1, 2 times f of 1, 3 is 1, 2 squared times 1, 3 squared. Those are both 2 cycles. So when you square them, you get the identity. So it's identity times identity, which is the identity. So these are not equal, meaning f is not a homomorphism. Okay, so that covers all the examples and non-examples I want to look at. The next thing is a specific theorem in your textbook, and specifically applying this theorem to some examples of homomorphisms. So the theorem is, I'll tell you what it says exactly. So formally, it says that f for a homomorphism f from G to H, f of A equals f of B if and only if A times the kernel of F equals B times the kernel of F. Note that the kernel of F is a subgroup of G. So here, A times the kernel of F and B times the kernel of F are cosets. Okay, there are equivalent conditions to this. There are so there's different ways of saying that A times the kernel of F equals B times the kernel of F. I'll list some of them. One is that A inverse B is in the kernel of F. That's a different way of saying that A times the kernel of F is equal to B times the kernel of F. 2, B inverse A is in the kernel of F. 3, A equals BX for some X in the kernel of F. And these are all like 3 is just a silly way of rewriting 1 or 2, because if A equals BX, you can divide by B and you would get that X equals B inverse A. So 3 and 2 are really just saying the same thing, but I guess there's a slight conceptual difference, because in 3, what I'm kind of saying is A can be the difference between A and B. Actually, yeah, maybe I'll just write 1 and 2. I changed my mind. And you can, so, but I'll just add the statement that you can think of A inverse B as dividing B by A on the left. So like I was saying before, division in a group, it's still division, but it has a direction. It matters. Do you divide on the left or the right? Do you multiply by A inverse on the left or the right in a non-abelian group? But you can still, it is still division in a sense that you can still cancel things out in an equation by dividing, but the direction matters. And you can think of B inverse A as dividing A by B on the left. It also works on the right. So these were all both on the left. You can also write B A inverse is in the kernel of F, or A B inverse. These are all equivalent to A times the kernel of F being equal to B times the kernel of F. So B A inverse is equivalent to dividing B by A on the right and AB inverse is dividing A by B on the right. And the proof of this theorem is actually not that hard. I mean, the idea of the proof is if f of A equals f of B, then just divide by A. F of A. So you just divide both sides by f of A. So you get, and again, there's a direction because it's a group. So I'll divide it on, let's say, the left, but the right also works. So I'll write that. So either the left or right. So I'll divide on the left. So you get f of A inverse f of A equals f of a inverse f of b. So you just get the identity is equal to f of a inverse f of b. This is the identity. And then f is a homomorphism. So everything goes inside f. Like if you have f of a inverse, if you have the inverse of f of a, that's the same thing as f of a inverse. And then f of a inverse times f of b is f of a inverse times b. So like the f can kind of just be moved around. So this is f a inverse f of b, f a inverse b. So this is because f is a homomorphism. So we have shown that f of a equals f of b if and only if, and it is an if and only if, because dividing by f of a inverse is a reversible thing, right? So I can go backwards. If f of a inverse b is equal to identity, I can multiply both sides by f of a and get back to f of a equals f of b. So yeah, so this holds if and only if f of a inverse b is equal to the identity, which holds if and only if a inverse b is in the kernel of f. And depending on whether you divide by f of a on the right or left, or f of b on the right or left, you get the other equivalent. So you get the other equivalent conditions, which are that b a inverse is in kernel of f, a b inverse is in the kernel of f, or b inverse a in the kernel of f. All of these are equivalent. So if one of them holds, all the others hold. And the proof is that. And then hopefully you can see why that's equivalent to the cosets being equal. And note this, I guess I won't prove it. I don't have time. But I could say it in words. I mean, the cosets being equal, a times the kernel of f being equal to b times the kernel of f, that means a must be in b times the kernel of f. So a must be b times something in the kernel of f, but then you can divide by a, so you get that a b inverse a, so you could divide by b, I guess. So you get b inverse a is in the kernel of f. I guess I could write that. So and note a times the kernel of f equals b times the kernel of f. So that implies that a is an element of b times the kernel of f, since a is an element of a times the kernel of f. So then a equals bx for some x in the kernel of f. And then you divide by b. So b inverse a equals x for some x in the kernel of f. So then b inverse a is in the kernel of f. So that's how you get the equivalence with all the other conditions that I listed. And then the point of this theorem, so the point is to apply this theorem to you can apply this theorem to the various examples of homomorphisms we had. So let's go back. What were the examples? I mean, one was f from r star to r star, taking x to absolute value of x. So what is the kernel of f? It's the set of x such that f of x equals 1. Well, it's the set of x such that f of x is the identity, which is 1 in this case, which is equivalent to absolute value of x equals 1, which is equivalent to x is either plus or minus 1. So the kernel of f is plus or minus 1. I mean, it's a set consisting of 1 and negative 1. That's what I mean. And then note that theorem 10.15 applies here. So if f of a equals f of b, or okay, f of a equals f of b, if and only if absolute value of a equals absolute value of b, and that occurs if and only if a equals plus minus b, or said differently, if and only if a over b equals plus minus 1. So that's exactly that's one of the conditions I wrote. Actually, so remember the conditions are you can divide by a on the left or a on the right or b on the left or b on the right, and they should all be in the kernel of f. Those are all equivalent to the cosets a kernel of f and b kernel of f being equal. But since it's an abelian group, division is just division. There's no divide on the right or divide on the left. So it's just a over b. And note that this is a step in the proof, right? Like absolute value of a equals absolute value of b implies that absolute value of a over b equals 1. But in a fraction, the quotient of two absolute values is the absolute value of the quotient. So, and that's exactly what we did in the proof, right? We just divided by f of a. And that's what we're doing here. We're dividing by the absolute value of a. So that's a good sign that our proof works. And it works in all the other examples too. So here's another example. F from Sn to the set of 1 and negative 1. And f maps permutation sigma to the sign of sigma. So here, the kernel of f is the set of all permutations sigma such that the sign of sigma is the identity, which is 1. So it's a set of all even permutations. So it's just an. So that's the kernel of f. And then again, theorem, what was the number? 10.15 applies here. So f of sigma equals f of tau means sine of sigma equals sine of tau. And then you can divide by sine of sigma on both sides. So you get the sine of the identity, or I'll just write 1, equals the sine of sigma inverse sine of tau. And I could have divided by the sine of tau as well. I just chose sigma. And this holds if and only if sigma an equals tau an. That's something I proved or I explained here. why the cosets being equal is the same thing as saying when you divide them, it's in the kernel. So the coset of A being the same as coset of B is the same thing as saying A divided by B with directions. So you should divide on the left here. If you're considering left cosets, you should divide on the left. Then it's equivalent to that quotient being in the kernel. Okay, so these are all equivalent. Last example. It's again on page 198 of your textbook. So here, F is a map from the multiplicative group of the complex numbers to itself, and it sends Z to Z to the power of 4. So kernel of F is the set of all Z that get mapped to the identity. So it's the set of all Z with Z to the 4 equals 1. So it's just plus or minus 1 and plus or minus I. And then again, theorem 10.15 applies. So if f of Z equals f of W, if and only if Z to the 4 equals W to the 4, and then you could divide, so you get, and this is exactly what we do in the proof. So if and only if Z over W to the 4 equals 1. So if and only if Z over W is either plus or minus 1 or plus or minus I. So for example, if f of Z equals f of the square root of 2, then Z over the square root of 2 must be either plus or minus 1 or plus or minus I. So Z must be either plus or minus square root 2 or plus or minus square root 2I. Okay, that's all I have time for this week. Actually, we got through everything, so that's great. Thank you for watching.